Hi friends, welcome back to my YouTube channel. In this video, we will see about thermal power calculation for the different gases. அதாவது இந்த காணொளியில் நம்ம தெர்மல் பவர் நம்ம எல்பிஜி இருக்கு இல்லைங்களா அதுக்கு ஹைட்ரஜன் மீத்தேன் அது போன்ற கேஸஸ்க்கு வந்து பார்த்தீங்கன்னா தெர்மல் பவர் கால்குலேஷன் அண்ட் ஃப்ளோ ரேட் அது எல்லாத்தையும் எப்படி கால்குலேட் பண்ணுறதுன்னு சொல்லிட்டு ஓவராலாக பார்க்கலாம். ஸோ ஐ வில் start in this Excel sheet. This is a simple Excel sheet. Okay, first I will create the naming or like something. I will make it. Okay, so let's consider the fuel type. Okay, fuel fuel name. Okay, next is for each and every fuel we used to take the value of low heating value, that is the amount of heat content available in the fuel. Okay, low okay, low calorific value. Okay, first fuel type, next column we can select the calorific value of the fuel and thermal power. Okay, thermal power. First I will take the LPG gas. So in the most of the industrial application or domestic application, even in our homes also, we are using LPG gases. So LPG gases is the gas which content propane and butane. So it is like 60 to 40 blending. So here the low heating value of the LPG gas is 46 megajoule per kg. So unit I will mention here. Megajoule per kg 46. Thermal power usually called in kilowatt. Okay. So okay. Then we'll consider the next fuel. So I will come to the calculation in later stages. Next, methane. Methane is calorific value is 50, and for hydrogen, hydrogen is 120. Okay. Now I will open one Google sheet. In Google, here we can see the calorific value of the different gases. Example: low value of LPG first. Okay, LPG in mega. Okay, here it's already there. Okay, for the cross verification, here we can see. Yeah. So LPG 46 megajoule per kg. I already mentioned here, right? So 46 megajoule per kg, small k. Okay, and methane 50 120. So here we can see methane is not available, but the value is 150. And yeah, so this is the one. Suppose we need to calculate the fuel flow rate requirement for the certain kilowatt. Example I will consider here, uh, 100 kilowatt. Okay, so here the thermal power is 100 kilowatt. Okay, for all the cases I will consider same. Okay, so here fuel flow rate in grams per second. Okay, the unit is in grams per second. So we need to calculate here. Suppose if you want to do any experiment or any burner design or any consumption of fuel calculation, we need to know how much fuel we are using. So this can be calculated simply based on the thermal power. So here definition of the thermal power. Thermal power. So I will like highlight in the different color to understanding purpose. Okay, thermal power is equal to low calorific value. Low heating value or calorific value. There are so many names. Low calorific value into mass flow rate of the fuel. So this is the very important formula. You should remember to calculate the fuel flow rate. Okay. So we can calculate. This is like a kind of a triangulation formula. Here we can calculate thermal power. Again from here we can calculate the mass flow rate also. Simple mass flow rate of the fuel here is simple is equal to thermal power then divided by the low heating value, low calorific value, sorry. So this is what the mass flow rate. So here now we are considering thermal power is constant. Constant means like 100. Suppose if you are designing a burner with 100 kilowatt, so I consider 100 kilowatt as it is. So how much fuel is required in terms of the different gases based on the grams per second? It is very simple. So we define this two formula, right? Thermal power and mass flow rate. From there we can calculate simply. Mass flow rate is nothing but thermal power divided by the low heating value. That's it. So we can calculate a reverse way also. Based on the fuel flow rate, we can calculate the thermal power as well as like from the calorific value also we can calculate the thermal power. Like that we can do any reverse way if you know these three parameters. Okay. Sorry. So these are the fuel flow rate is coming. So here I would like to bring one more like a parameter. Sorry, one more flow rate in terms of the volume flow rate. Most of the research people used to do based on the SLPM. That is like next parameter I will define here. SLPM is like volume flow rate of the fuel. Okay, so it's nothing but the standard liter per minute. Okay, so this is what. So here we need to convert this because most of the researcher used to do based on the SLPM or some they will use the grams per second also. So why I am here doing conversion from grams per second to SLPM is to understand how much volume, because physically in order to keep the number of cylinders for the hydrogen and methane or LPG, how much cylinder volume we need to keep in this particular space. So that's what. So why I am bringing this concept is it is very important for the storage point of view. Example. So for that one, we should know the density. Okay. Okay. Let's consider density kg per meter cube. Okay. So I know all the density value. Example, this is LPG is 2. This is 0.75 something. So I will check in verification in the Google 0.08. So these are the different densities. So here, based on this one, we can see hydrogen having the very lowest density. Okay, so this is sure, this is sure. Just for the cross verification, I have small dot methane density. Okay, so let's check with the internet also. Density of methane. Yes. Okay. The general methane gas is 0.657. Sorry, 0.657. Okay. So I need to convert into the same shape. So to select, I mean like same font size or same font. So select the previous font size on shape and you do like that. That's it, simple. The paste option will be there, right? That is format painter. Okay, it will do the format. Okay, so this is the density. So here we have the formula. So here we are converting mass flow rate into the volume flow rate. So that is called the SLPM. I mean like volume flow rate also we can tell. So fluid flow rate in SLPM unit. Okay. Okay. So this is simple. I will tell formula. First, we need to use the mass flow rate divided by the density. Okay, into 60. Just we are converting, so like mass into the volume. So here we can see for the same amount of thermal power, we are having different densities. Sorry, different, because of different densities, we are having different SLPM. Okay, so here what I'm trying to bring here is concept. Example, now it's like one cylinder. So example, I will go. So one cylinder capacity, let's consider. Capacity is like, first I will consider 65. Okay, let's 65 to 1. Okay, this is the volume, one cylinder capacity. Okay, so in order to achieve the same thermal power, here we need to I mean like, let's consider the, this is for just understanding purpose I'm giving. The 65.21 is the volume capacity consider. Okay, so this is like a number of cylinder calculation. Let's consider this is like per minute it's consuming 65. Okay, then this divided by, f log into, okay, 1. So here we can see per minute. So 1 minute it's considering, it consuming only one cylinder. Okay, for the same thermal power calculation here, whereas for the methane we need around 3 cylinders. So you consider like how much volume, like space we require. Okay, similarly for hydrogen we need 9.5 cylinders. Same volume capacity of the cylinder we need around 10 cylinder. So from this concept, what I'm trying to bring is, to burn the same thermal power, we need to have the number of cylinder is more for the hydrogen. In practicality also, it is the true. So we done most of the experiments with hydrogen as well as the LPG. So for the same thermal power, we are using more number of cylinders for the hydrogen, whereas with the LPG, we can use very less compared to the hydrogen as well as the methane. So this is the simple calculation. Here I would like to conclude. Before concluding this section, I would like to give the again summary. So first, we are writing the different fuels. Okay, different fuels. Okay, put all water. Then we need to know the low calorific value or low heating value of the corresponding fuels. Example LPG. LPG we will select with some different color to understand purpose. Okay. Then this is the methane. Methane I will select one more again different color, and hydrogen. Hydrogen also, like people are telling green hydrogen is there, like so I will just for representation putting green color. Yeah. What I'm trying to say is, in order to calculate the thermal power, we should know the two quantities. One is low calorific value, another one is the fuel flow rate. Otherwise, if you know the thermal power and calorific value, you can calculate the fuel flow requirement for the corresponding thermal power also. So this is a simple cases. Okay, for the three different fuels. Similarly, you can calculate for the n number of fuels. Uh, so here we have learned two different important formula. Sorry, one important formula. One is thermal power. It's nothing but the low calorific value into the mass power. Okay, this is how the simple calculation. I next. Okay, sorry, I forgot one section here. So now I will move to the blending percentage kind of like, okay. So suppose if you want to blend some other fuels with the other fuels, I will give some small example. Okay. So total volume is this one, right? Uh, Blending. So blending can be calculated based on the two parameter. One is thermal power and another one is volume based. So here example for that one I will select a new sheet. So I will carry on here itself. Okay. So here, okay, first I'll start from here itself, like that is very simple. Total thermal power. Okay, I will consider only two fuels right now for LPG and methane. Okay, and this is thermal power. I will consider under. Okay, I will calculate for the different percentage. Here first, with the based on the thermal power. Thermal power for the different percentage. Okay. So 100. So thermal power I will keep constant. Okay. For all the cases, let's consider around 10 cases, 11 cases, whatever maybe. Here, so I will calculate the like a thermal power for the different percentage. Okay. Let's first 100 percentage. So 90 percentage, 80. So like that. Okay. So this is thermal power in kilowatt. This is LPG thermal power. Okay. This is methane. Okay, I will consider hydrogen. Sorry, hydrogen. Okay, kilowatt. Okay, then so this is a total. We are having 100 kilowatt here itself. Means here it will be zero, right? 90, 10, 20. Okay, that's it. So this is based on the thermal power blending. Suppose for this one we can calculate the volume based also. Okay, so this is like a fuel blending calculation based on the thermal power. Okay, next I will calculate based on the volume. Okay, same only I will put copy here, paste it here. Okay, sorry, I will paste it here. Okay, same THCR thermal power kilowatt. Okay, so for that is 100 is constant. I'm just for keeping understanding purpose. Then LPG volume, LPG here hydrogen. Now we are considering LPG as a base. Okay, then in order to achieve 100 kilowatt of thermal power from LPG we calculated, right? So that is 65. Okay, sorry, volume flow rate SLPM. Okay, okay, so here - 46. Sorry, first I will calculate the grams per second. So grams per second is like a simple formula. I will use that one divided by 40. Okay, and then from then I will calculate to the volume flow rate. So again divided by density into 60. Okay, okay, got it. So here like that. Okay, this is SLPM. Okay, this is a total SLPM. Okay, suppose if you want to blend hydrogen with LPG, so it should not be more than 65 SLPM. Okay, that's like a basic criteria, because if you are replacing with the 65, more than 65 of this one, 65 SLPM means it's like higher than the flow rate required for this one calculation. Okay, let's consider for the different category and I will calculate based on the SLPM thermal power how it's changing. Okay, then it has to be 0, right? Okay, next I will give 55. Okay, I will consider for the name check. Okay, okay, it's coming correctly. Okay, 33, 22, 11, 5, 0. This is for the like a simple understanding purpose. Okay, here we can see volume and volume. This is replacing only volume. Okay, so total volume is coming. Okay, by percentage I will calculate here. Okay, sorry, I made one mistake here. I will do it again. 100. Okay, sorry, I forgot to add into 100 to understanding full percentage wise. Okay, so this is how the volume percentage is coming for the different volume. Okay, so now this is the volume percentage blending. From this, I would like to calculate again back to the how much thermal power is coming based on this volume. Okay, let's consider for the 92 percentage of the H2 volume, how much thermal power is coming when compared to the like LPG. Okay, this is percentage. Okay, this is for just understanding purpose. If you want more details, please comment. I will like to give more detail about this one. Okay, so I will like to calculate the again uh, H2 into grams per second, because in order to calculate the thermal power we need to in the grams per second, right? So that is very simple. So SLPM of hydrogen, sorry, this one into density divided by 60. Okay, okay, this is how it's coming. Okay, then I will calculate the H2 thermal power. Okay, that is very simple. We know the grams per second into the low heating value. Already mentioned that that is like a 120 for the, sorry, accept it. Okay, so in this I need to calculate percentage wise, percentage H2 percentage thermal percentage. Okay, thermal power percentage. Okay, yeah. So overall percentage is like, sorry, Yeah. So this divided by the overall thermal power is how much? 100, right? Yeah. Sorry, I need to log the A. So that means like if you supply 100 percentage by volume, replacing the LPG also, we will get just 10 percentage, 10.14 percentage of the thermal power only by the volume replacement. Okay, this is very important. Okay, let's consider here for 500, it will change all the stuff. Okay, so this will be like you can do like conversion very easily. Yeah? So this can be easily understandable. How much percentage wise contribution? Because 100 means I'm getting confused like because like both are it's like in the same percentage wise. 100 divided by 100. So here we can see in the overall uh, by volume wise. So if you're replacing 65%, sorry, 100 percentage of LPG also, we will not get that much of the thermal power. That we need to understand. Okay, so here it is very clear that so in order to achieve the same thermal power for 500 by replacing the volume of hydrogen is not at all like satisfying the criteria. Okay, so here in order to achieve the same thermal power we need to supply more than 100 percentage of the volume of the LPG. So this is how the main conclusion is. Thank you so much for watching this video. If you have any doubt regarding this calculation and all, please feel free to contact me. Thank you so much for watching this video. Bye.